All right, we are on text section 4.3, and this is actually chapter 14 in the JV Stats curriculum. Pretty cool. We're doing conditional probabilities. It's actually done several different ways. I got some cool things I'll show you, which will be nice, just different maps or drawings of ways of handling stuff. You'll like it, I think. So, as always, I say, stop the video anytime so you can get the answers, repeat it, whatever. Probability has a tendency to be difficult, so I try to do this real slow and show you all the steps, okay? So conditional probabilities means the conditions have changed. I mean, that's obvious. Here is the formula for it right here, which I will circle again right here. Here's the formula for it, okay? This line means given that. So that will read B given that A occurs. Could be if, B if A occurs, probably even simpler. Okay, if. All right. And it really functions as kind of a fraction bar where if you look at it that way, A is the denominator and then B will be the numerator in part. It's actually the intersection of A and B. That formula right there can be confusing. I think if you use common sense, I think you'll be okay on this. So let's just go with question A here, okay? All right. So we're on 1A, and it goes, see, there you go. We're on 1A. All right, so in 1A, we got a standard deck of 52 cards. Find the probability that one card drawn is a 9 given it's red. So the given is the denominator. As you can see, it's 26 instead of 52. Because if it's not one card's a 9, it's one card's a 9 given that it's red. So you have to ask yourself, what are the chances it's red? That's 26 card, that's the bottom. Now, one card is a 9 given it's red. We need the intersection, if you look up here, of 9 and red. There's two of those. There are two. You see my fingers. There are two of them. Red of hearts and red of diamonds. So that's how you get that. Okay. So if you just have red cards, 26 of them, what are the chances you get a 9? 2 out of 26. Okay. Just break it down and simplify it to yourself. All right. One card drawn is a spade given it's black. All right. So how many black cards are there? That's the denominator, 26, as you can see by my arrow. And how many of those 26 are spades? That's the intersection of spade and black. That's why that symbol's right there. Intersection of spade and black. If you remember, upside down U is intersection, where there are both. There are 13 spades. Ace of spades through the king of spades. So if you have a black card, there's a 50% chance it's a spade. Simple. Okay. Item 3. Okay. One card drawn is black, given it's a spade. Okay. Given it's a spade, what are the chances it's black? Well, how many spades are black? All of them are. So that's where you get this one right here. And I even put the notation in there with the given that being the line. Okay. Next one. 3 cards are drawn. The third card is the first black. Okay, so here we go. The conditions are changing. First draw is 50-50. Then if you don't get a black on the first draw, your chances, then you have to draw another red. So this is the second red. 25 of the remaining 51s are red. Then you finally get the third one is black. There were still 26 of them left. Okay, so there we go. All right, good. An Easter egg hunt has 8 eggs with candies, 10 eggs with toys, and 5 empty eggs. Find the probability that you want one egg with the toy. Okay. So toys. All right. So there are 23 total. So that one's pretty simple. Nothing really conditional about that. But the next one, the first 3 eggs all have toys. Okay. The conditions are changing here. Okay. So 10 out of 23, then 9 out of 22, and 8 out of 21. So it's about 7%. Okay. Sound good? And then item 3 is the first 3 eggs found are not all toys. Well, in that one, you're just going to take the answer that we had here, put it right there, and go 1 minus. Remember, the complement will give you the opposite. It's a pretty good chance, about a 93% chance they won't all be toys. All right. The 5th egg found is the first empty one. The 5th egg found is the first empty one. All right. So there's 5 empty ones, right? That'd be terrible to get an Easter egg hunt. You have empty egg. Okay, so the 5th one is the first empty one. All right, so there's an 18 out of 23 chance you'll get something in it. Then the second one will be 1722 as we count down 1621, 1520, and finally 5/19. So this is all conditional probability because the conditions are changing, but it doesn't really go off. Well, that was pretty bad. It doesn't really go off of this formula this time. Okay. All right. Now the next one is another way you could see conditional probability. And I would, really invite you just to try to use common sense on all this stuff. Okay. I like this one because you can see the intersection of stuff. All right. And it's kind of overkill the way I'll do it, but that's okay. Find the probability that a random selected person is in high school or has a pet. Okay. Is in high school. Okay. So is in high school is all of these added up, okay, which I believe is 11, right? 11, or has a pet, all right? And pets, you could have obviously 1 pet, 2 pets, or 3 pets, okay? So there's lots of ways to do this, but it says or has 1 pet. Okay, or has 1 pet. Okay, 8, 10, 13, right? Notice -2. You can physically see the intersection. You can physically see that. Now, let me remind you of a formula that we broke out earlier in this section, which is not on this lesson. When you do an OR problem, that means add. You do probability of A plus probability of B, and I would write this down above this chart, minus probability of A intersection B. Does that make sense to you? Of A intersection B. All right, so in that case right here, the intersection you can physically see is 2, so you got to subtract that out or you double counted it. It's really cool to see that. That formula just comes alive. Please write that down on the top of your notes so you remind yourself of that formula. Okay, and that means intersection right here. It means intersection. All right. All right. In elementary, and has 2 pets. Now, and means multiply if they're independent, but I don't think this chart's independent. So this and means 2 different qualities. It's a 2-way table. In elementary, and has 2 pets, which is right there, 6. And by the way, the total on this table is 44 if you add the margins up. I didn't do that for you. Okay, so that's pretty easy. And then here we go. In college or has 0 pets. That would make sense. College kids usually don't have pets because they're in college. Okay, in college, okay, or has 0 pets. All right. So I'm going to add these up, 7, 10, 11, 12 right there. 0 pets, 7, 10, 14. But I got to subtract out the intersection, which is 7 of them. So most kids don't have a pet in college. Maybe they have it in their dorm room, like a little lizard or something. I don't know. Not really sure. Okay, cool. Now, let's go to the next section. Diagrams. Oh, I love these. I just absolutely love these. Are so fun to do. Okay, this is hard to fit on the screen, but we're going to give it a shot here. All right. So when you're doing statistics, typically Venn diagrams are going to be used, and please write this word down, when the word both is involved. And then it works out. Tree diagrams are typically for independent events. Okay, independent events. The Punnett square is another way of doing the tree diagram. Usually, it's typically biologists do the Punnett square because they do, see how it says A exponent C, that's A complement, and then B complement. That's typically what they do in biology. But in stats, we use tree diagrams or kind of flow charts, what happens. So we don't usually use this, but I have it there just to show you what you could do. Okay, so let's see what we're going to do here. All right, let's give it a shot here. All right, and slide down here. Perfect. Yeah, got it. Perfect. All right, so let's look at 2A right now. All right. In any given month, the local hospital performs 2 surgeries. 65% of the surgeries are A, and the rest are B, which is 35%. Surgery A has a 95% success rate, B is 80%. Find the probability that a randomly chosen patient. Okay. Now, it doesn't say the word both in here, and it doesn't even say independent, but I think you're going to have to assume, we do a lot of assuming in math and statistics, that A and B are just separate types of surgery. Okay. So I'm going to do a tree diagram. You could do a Punnett square if you have a background in that. So check it out. Here we go. Notice 65% are A, 35% B. That's the first step. Now, A success rate is 95%. Notice that 95 right there. And B, not successful would then be 5%. So if you multiply it out, you'll get, let me change colors here real quick so you can see this pretty good. This one is the probability of you doing surgery A and it being successful. This is doing surgery A and not being successful. Notice these two numbers add up to 65%. All we're doing is dividing 65% into 2 categories, successful and not successful. Okay? And the same thing goes for B. B has got an 80% success rate. Okay? 20% not successful. And then you're going to multiply those through and you're going to get these 2 numbers. Okay? So the probability of a success. So that's going to take you 10 minutes. You probably got to stop the video and write that down. So this says had a successful surgery. So successful surgery would be this branch and this branch right here. So let's add those 2 up and you'll get 0.8975. Okay? Pretty cool? Now, the second question, there's all kinds of questions you can ask in these. I only asked 2 here, but had a successful surgery given it was category B. Okay, given it was B, 35%. What are the chances and it was successful, which is 0.07. Notice you go backwards and you get the question. We already know that 20% were successful, but it's kind of cool to see that. All right. There's lots of other questions you could ask. I ask more in an AP class than I do here, just so you know. We're just trying in this class to get you to do the tree diagram right. All right. All right. Question B. 70% of LQ students are enrolled in a foreign language, 45% are in art, and 30 are both. Okay, 30 are art. There's the word both. So that kind of tells you that we have a situation where this is a Venn diagram. And you have to, if you wanted to check if they were independent, you can real quick. It's really easy, okay? So if 70% of the kids are enrolled in a foreign language, 0.7, and 45% are in art, okay? And what you're going to ask yourself is, does that equal the both section? So I'm just going to multiply and grab my calculator in my hand, which you probably can't see. 0.7 times 0.45, and you get 0.315. So they're not quite independent, which is why we're not doing a tree diagram. Okay? So we're going to do a Venn diagram on this. Now on the Venn diagram, always start in the middle. Start here. Okay? So I put the 30 there. Now, foreign language is FL up here. Notice I put a 40 there because 40 plus 30 has to be 70% for the total bubble in there. Okay? And then in A, 45% are in art. Only 15 are in art alone. 30 plus 15 is 45. Then I'm going to add these three numbers, which I'll circle in a different color here. Going to add these three numbers. And 40 and 30 make 70, and 15 is 85. So 15% are in neither. They're in neither of them. Okay? So let's ask these questions. There's actually 4 parts to a Venn diagram. The 4th part is the neither part. Okay? Only a foreign elective, only is that one. Neither is this one. Okay? Only an art elective is that guy. And a foreign language, given he's in art. Oh, I absolutely love this question. It's not as obvious. A foreign language given he's in art. Let's start with given that he's in art. So we're in this bubble. Given he's in art is 45%. And then of only that bubble, how many are also in a foreign language? 30 of the 45, so it's 2/3 or 67%. So wait. Okay? Last one. You can see the Venn diagram is the choice here, but let's check it out. Okay. I'm going to make this a little bigger if I can. So just hang on one second. Let's see if that works. I think it does. There we go. Okay. So let's try this one. 12% of teenagers own both an iPad and an iPhone. Well, 26% only own an iPhone. 42% do not own either an iPad or an iPhone. Find the probability of randomly selecting a teenager who owns an iPad. Fine. Okay. Let's just start with this. Okay. So I think the word both shows up. I mean, I guess there's ways to write these where both don't happen, but it says it right there. Both. I'm going to start in the middle with both, 12. Now, 20% own only an iPhone. So I don't have to subtract out because they had put the word only in there. So 38% own an iPhone, by the way. 42% do not own either an iPad or an iPhone, okay? So when I start this process, I didn't get that number. So I had to add up 42, 12, and 26. That gives me 80. And then I went 100 minus 80, and I was able to get the 20. Just so you know how I got that. Okay? Now, owns an iPad. iPad is these two added up. So it's 32%. Owns part B here, or 2. Owns only an iPad only, no iPhone. An iPad only, no iPhone. Okay, an iPad only, that's 20%, that one right there. Okay? Roman numeral 3. Owns an iPhone or an iPad. An iPhone or an iPad, that's going to be all 3 of these added up. Okay? There's actually a couple of ways to do this. It's kind of interesting. You could go 26% plus 12% plus 20%, right? Or you could do 1 minus 0.42. Or you could do, if you had the numbers differently, 38% plus 42% minus the overlap, which is 12%. Remember how you subtract with a double count? Another way to do it is, I showed you 3 ways. I mean, I don't know which one's easiest for you. And the last one is owns an iPad given he has an iPhone. All right, given that he has an iPhone, I'm only in this, whoops, I moved it. I'm only in this bubble right here. Given that he has an iPhone, okay? So that's 38 down there. And then owns an iPad. This part of the bubble owns an iPad. So 12 out of 38 ends up being about 32%. All right, pretty cool. So there you have conditional probability with some other stuff mixed in. Thanks for watching.